Welcome to lecture number 23. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course, Geosynthetics Engineering in Theory and Practice. This module 5, lecture number 23, Geosynthetics in Pavement. The recap of previous lecture, we have gone through the stress reduction to downwards with the depth of the granular field, advantages of unpaved road, design chart of US Forest Service or USFS for unpaved road, US Forest Service design curve, modified California bearing ratio, that is CBR test, or design of the pavement thickness without Geogrid, that is as per Indian Road Congress 37-2001. Now, I will focus the design of reinforced unpaved road given by Geogrid and the Hand 2004. Step 1. Calculate the radius of equivalent contact area using the following equation. And R is equal to root of P divided by pi of small p, where R is the radius of equivalent tire contact area and P is equal to wheel load kilonewton and P is the tire contact pressure kilopascal. Step 2. Calculate the California bearing ratio of the subgrade soil or undrained cohesion of subgrade soil, that is Cu is equal to Fc into CBR Sg. So, Cu is undrained cohesion of the subgrade soil, Fc factor equal to 30 kilopascal and this is CBR Sg is the subgrade California bearing ratio, that is less than 5. Step 3. Calculate the allowable bearing capacity of subgrade soil without reinforcement. So, if you use this equation, P of H0 unreinforced is equal to S by Fs pi r square Nc into Cu is equal to S by Fs pi r square Nc into Fc into CBR Sg. You are substituting this value Cu is equal to Fc CRG. So, Cu is equal to, you put this substituting this value, that means Fc into CBR Fg. So, where S is equal to allowable rod depth is equal to 40 millimeter, Fs is the factor equal to 75 millimeter, R is the radius of equivalent tire contact area, Nc bearing capacity factor equal to 3.14, Cu undrained cohesion of the subgrade soil and CBR Sg subgrade California bearing ratio. If the wheel load is greater than the allowable bearing capacity of the subgrade soil, a base course is required without or with geosynthetics material. Now, to calculate the base course thickness, the following steps should be followed. Step 4. Determine the limit modulus ratio, that is R of E, and the modulus ratio factor Fe. So, Re is minimum of EBC by ESC, 5.0 is equal to minimum 3.48 CBRBC whole to the power 0.3, 5.0. So, EBC is the base course resilience modulus, ESG subgrade resilience modulus and CBRBC is the base course California bearing ratio and CBR RSG, you know, that is subgrade Californian bearing ratio, and the modulus ratio factor Fe will be equal to 1 plus 0.204 Re minus 1. Step 5, determine the bearing capacity mobilization coefficient M in terms of the thickness H. So, M is equal to S by Fs 1 minus 0.9 into Exp minus R by H whole square, where M is the bearing capacity mobilization coefficient and S is allowable rod depth in millimeter, and H should be greater than 50, less than 100 as per 2004, and Fs is the factor equal to 75 millimeter, and R is the radius of equivalent tire contact area meter, and H is the thickness of the base course. Step 6, determine the required base course thickness. So, you have to adopt this equation, H is equal to 0.868 plus 0.661 minus 1.006 J square into R by H whole to the power 1.5 log n divided by Fg into root of P divided by pi R square M into Nc into Fc into CBR Sg minus 1 into R, where the J is the aperture stability modulus of Geogrid, that is Mn per dig, that will be less than 0.8, and J is 0 for geotextile and in unreinforced case. H is equal to thickness of the required base course in meter, and P is the wheel load in kilonewton, and Nc is the bearing capacity factor, that is 5.71 for Geogrid, and Nc, if you use geotextile, the Nc geotextile will be 5.14, and in case of unreinforced, Nc unreinforced will be 3.14. So, from this equation you have to calculate the what will be the base course thickness required, and this calculation of base course thickness need iteration. So, what is to be done with this equation? This is important, this equation, and how you can calculate the thickness. So, if the calculated H value does not match the assumed H value, so you assume some H value, and if it does not match with this, you can see here also H, here also H. So, you have to calculate H value that does not match the assumed H value. M value is to be recalculated and is used as the assumed value of the next iteration. The process is to be repeated until the calculated value is approximately equal to the assumed value. So, you have to continue, you have to repeat. I will show you with one of the example. Step 7, determine the reduce in the base course thickness using Geogrid or geotextile, that means delta H will be equal to H0 minus H, or H0 is the thickness of the required base course for unreinforced case in meter, H is equal to thickness of the required base course with Geogrid or geotextile in meter. So, this is one example, 2-lane carrieway road, plain terrain, and number of commercial vehicle as per the list count P is equal to 1000, axial load 81.6 kilonewton. So, wheel load will be half of the axial load, that means 81.6 by 2 is about 40.8 kilonewton. tar pressure P is 500 kilopascal, subgrade severe is equal to 2%, traffic loading category E is 450 to 1500, that is CVD, commercial vehicle per day, and number of the years between the last count and the year of completion of the construction X is equal to 5 years. Annual growth rate of commercial vehicle R is equal to 10%, and design of the life of the pavement after completion is equal to 15 years. Now the solution. So we adopt initially the design as per IRC 372001 only for the unenforced condition. We have earlier shown you this equation for IRC. A is equal to P into 1 plus R to the power X into D, and also we have shown that what is NS value 365A into 1 plus R N to the power N minus 1 by R into F. So where D is the lane distribution factor, that is 75%. You can see the lane distribution factor. This you can have the lane distribution factor that you can have from the table, that is 75%, and then also the F, that is the physical damage factor, that is 5.5. Actually we have shown it earlier that physical damage factors here, that physical, that is what you call physical damage factor. So damage factor is 3 point, we say the terrain, plain terrain we consider, and the CVD is between this 150 to 200, that's why the 3.5. So from here we have taken this value, that what is the physical damage factor, this is 3.5, and also this is D we have calculated, and also the 2 lane single carriageway road, and that's why the lane distribution factor we have taken about 75%. Okay? So we have taken this is 75%, and we have taken this is physical damage factor is 3.5. So this way we have calculate that what should be the will be the D as well as what should be the F factor value. F factor value. So here is the D. That means D lane distribution factor, that is 75%, as I showed you in the table. Similarly, F is the physical damage factor, that is 3.5, that is as I showed you in the table. So you know the D, you know the F. So you can calculate what is A. AP is given 1000. 1 plus R is also given in our problem. R also it is given is 10%. So this is 0.1. P also it is given. We have that 1000 here. So P is 1000. 1 plus R is, I told you it is given, that R is 10%, that means 0.1. This is 0.1 whole to the power X. X is given 5. You can see that X, this is X, this is X, the number of year between last count and the year of completion of the construction, X is 5 years. So this is X5 into D. D is this 75%, 0.75. So you can calculate this A is equal to 1208. Similarly, you can calculate NS. NS is equal to 365 into A we obtained 1208, so this is 1208 into 1 plus again R is equal to 0.1. Here you can have the R 10%, as I say annual growth rate of the commercial vehicle is 10%, R is equal to 0.1 whole to the power N. N is how many years? That means 15 years. We have considered the design life of the pavement completion N is 15 years. Okay? So we have taken this is 15 minus 1 divided by R. Again R is equal to 0.1. This into F. F is equal to physical damage factor. This physical damage factor we have calculated from the table, that is 3.5. This is 3.5. So if you calculate, you will obtain NS value is equal to 49.03 into 10 to the power 6. So that means you can take approximately NS value is equal to 50 into 10 to the power 6. That means 50 million standard axle, which is called MSA. That means 50 MSA. Most of the time we will use this term, so you could remember this MSA. So NS is equal to 50 MSA. So now you know that this is the chart, design chart for the determination of the pavement thickness. Traffic lies between 10 to 150 MSA. Okay, I say that MSA, remember, million standard axial. This is million standard as per IRC 700. So you know now what will be the design traffic. So your NS value is known is 50 million. So this is you known 50. Now you know that what will be the CBR value. CBR value is 2%. So you move up, you can see that here that we record subgrade CBR is 2%. So from this design chart, knowing the value of traffic, that is 50, you move up. This is for CBR 2 curve. So it touches this curve when the CBR is 2, and then you move horizontally, and which will give you that what will be the thickness of the unreinforced pavement in terms of the millimeter. So it maybe lies between 900 to 1000, and this value will be approximately 925 millimeter. So from this design chart, for 2% CBR and 50 MSA standard axial, then total pavement thickness will be 925 millimeter or 0.925 meter. So when you will design for unreinforced course, you know that what will be the thickness of the pavement. So as per IRC code specification, so this total thickness of the pavement is 92.5, this is centimeter. So this is the cross section of the pavement. This is the soil subgrade, whose CBR value is 2%, and traffic is 50 MSA. That is, you know, that million standard axial, and axial load is 81.6 kilonewton. So this thickness of the pavement we calculated 92.5. Now as per IRC code specification, you have to provide with the bituminous surfacing codes. You can have in the IRC code that how you can distribute this. Bituminous surface codes is about 1.5 millimeter, 46 millimeter is the sub base, and this is about 25 millimeter is the base course, and 17.5 millimeter dense bituminous macadam, and 4 centimeter bituminous concrete. So this way you are to show the cross section of the pavement. So what bituminous surface is about 21.5 centimeter, bituminous concrete BC is 4 centimeter, and bituminous macadam is 17.5 centimeter. So you can design that. Now that design as per Geogrid and Han 2004 without and with reinforcement. So you can see here that what will be the input data and what should be the value. So axial load Q kilonewton 135. So wheel load P will be the half of this. This is 67.5. Tower pressure kilopascal P is 500. Radius of equivalent contact area meter R is 0.207. Base course CBR percentage and CBR BC is 20. CBR of the subgrade soil percentage CBR RSG is 2. Allowable rod depth millimeter small s is equal to 40. This factor KPA FC is equal to 30. Factor FS KPA is 75. Geogrid aperture stability modulus. This is important. J A main part. This is 0.65. Number of axial passes N is equal to 50 into 10 to the power 6, and bearing capacity factor NC unreinforced is 3.14. NC Geogrid is 5.71, and NC for geotextile is 5.14. So we have used both type of the material, geogrid and as well as geotextile material. We will see that what will be the thickness of the pavement with geogrid and as well as with geotextile. What will be the reduction of the thickness, that we will check. Now this is output user interface for unpaved road in the unreinforced condition. So unreinforced condition, assume the base course thickness, as I told you that earlier equation, you assume something value, H assume in meter, you assume 0.3, whatever it may be, you can assume. And limited modulus ratio RE is 4.274, to modulus ratio factor AP 1.668, bearing capacity mobilization factor M 0.235. This how it is all the changing, but you have to do with the iteration. And then you can have what will be the required base course thickness. This is H final. So this is by the iteration. You can see if you do the iteration, and then you can have this value for unreinforced case. This is as per Geogrid. So this is 0.87 meter. You can see this is gradually it is increasing, then it is stabilized when this is matching with 0.87 and 0.87. You can gradually see that this is the end, then it is finished. So this is by iteration you have to check that what value it should match with the left to the right. So you can see for unreinforced case this value will be 0.87. So therefore we can say that the thickness of the unpaved road in unreinforced case will be 0.87 meter. Now for unpaved road with geogrid. So assume the base course thickness, again H assume, okay. So like this, limit modulus all are, it is there, moduli ratio is there, bearing capacity mobilization is there, and the required base course thickness H final. You can see by the iteration left to the right, and you can see 0.37, you can see 0.37. It is matching here, then it is finished value. So with the geogrid material, you can say the thickness of the pavement with geogrid in unpaved road is 0.37 meter. Whereas you have seen earlier in case of the unreinforced 0.87 meter. In case of the geogrid it is 0.37 meter. Now if you use the geotextile material, okay, and you can see here that in case of geotextile material it is thickness is 0.67. You can see it is matching here 0.67. This is by all iteration. So with geotextile is 0.67 meter. So for the geogrid enforced unpaved road, a factor of safety is considered 1.5. So you can check what will be the percentage of saving in percentage. Now thickness of the base course of unreinforced unpaved road, that is H unreinforced, is 870 millimeter, which we calculated from the table. Now thickness of the base course with geogrid, that is H geogrid, is 370. We have shown that here, that is 370. This is unreinforced 87.87 meter, 870. Then geogrid is 0.37. That means here is 370 millimeter, and with the factor of safety 1.5 we consider. So this will be the 555 millimeter. Now thickness of the base course with geotextile, that is millimeter, H geotextile is 670 millimeter. This is here 670 millimeter. This is 0.67 meter, 600. So percentage of saving with the geogrid will be 36.21 percentage, and percentage of saving with geotextile will be 23%. So geogrid and the geocomposite layer are to be provided in between the subgrade and the subbase layer. Geocomposite layer will drain out the infiltrated water from base course and the uplifted water from the subgrade. Base course thickness using geogrid is 55.5 centimeter. You can take approximately 56 centimeter. Pavement composition, geogrid reinforced. So bituminous surface reference to IRC course 37, it will be 21.5 centimeter. Surfacing consisting of 4 centimeter bituminous concrete, that is BC, and 17.5 centimeter dense bitumen macadam, that is DBM. In the base course, we provide 20 centimeter water bound macadam, WBM, that is 20% of CBR. In sub-base course, 35 centimeter granular material of CBR, not less than 30%. These are all according to IRC code specification. So ultimately we are showing this pavement section where traffic N is equal to 50 MSA and axial load is 135 kilonewton. You can see that unreinforced case, this is the soil subgrade, this is CBR value is 2%. So this is the thickness of the pavement, that is 108.5 centimeter, and this is 60 centimeter for the subgrade, 30 centimeter for the base course, that means 20% of the CBR, and 17.5 centimeter dense bitumen macadam and 4 centimeter bituminous concrete. But in case of the reinforced with the geogrid, where soil subgrade CBR is equal to 2%, the thickness of the pavement is 76.5 centimeter, and this is 35 centimeter subbase, 20 centimeter base course, that is 20% CBR, and 17.5 centimeter dense bituminous macadam or DBM, and 4 centimeter bituminous concrete. So here is the geogrid is placed between the aggregate and the subgrade course, this red line. Apart from this geogrid, you have to provide with one geocomposite material which will act as a drainage and the filtration. This is essential because you are putting this geogrid material, it will act as a reinforcement, whereas geocomposite material, if you put with along with the geogrid material, either it is a woven and non-woven geotextile material and laminated also with the geogrid, this whole will be as a geocomposite material, which will act as a very good drainage and the filtration material. So it will solve all these problems. Here you can see how the thickness of the pavement has drastically reduced due to the introduction of the geogrid or the geotextile material. This is the some section. You can see that as I say that by geocomposite material, there is water may flow up and down, and then there is a possibility for water should be drained it out to the drain. So if we provide with the geocomposite material, then it will act as a very good drain, because drainage is very important. Most of the time water is stagnant and road is deteriorated because you don't provide proper kind of the drainage system. So if we provide with this some geocomposite as a drainage along with the geogrid material, then it will act as a very good drainage. Because there is a possibility for excess pore water pressure development, some water may move in the upward direction, or due to the rain, then water can percolate through this geocomposite material. So it will act as a separation as well as it will act as a drainage and the filtration. So this is the pavement design system we have to be. This figure shows the relationship between equivalent reinforced base thickness versus non-reinforced base thickness. Now here geogrid reinforced base course for paved highway given by Carroll et al. 1987 based on the experiment, and it can be observed from this experimental result that a 250 millimeter geogrid can be introduced either at the bottom or at the top of this level. That means geogrid at the bottom of the base layer or geogrid at the midpoint of the base layer. So, this under the equivalent reinforced base thickness of 250 millimeters. So, this is based on his experimental result. Now, I will explain the Ostrow 1993 design method for flexible pavement. Now, design problem: a flexible pavement for a road 2 lane each direction need to be designed for 25 years life. Average subgrade CBR is equal to 2%. Expected traffic, that is tandem axial 36 caves, 1 lakhs per year. Number annual growth rate to be considered. Terminal serviceability PT is equal to 2.5. Reliability level capital R is equal to 95%. Standard deviation S0 is equal to 0.35. Asphalt layer coefficient AI is equal to 0.40. Base course layer coefficient A2 is equal to 0.14. Subbase layer coefficient A3 is equal to 0.08. Drainage condition is good. Pavement is exposed to saturation moisture more than 25% of the time. Now, we will solve this problem. This is solution without reinforcement. Step 1, determination of W18, that is W18 is predicted number of 18,000 pound equivalent single axial load, or that is ESAL application. A, for tandem axial 36 caves, PT is equal to 2.5, that means terminal serviceability is 2.5, and assume SN structural number of 6.0. The axial load equivalency factor is equal to 1.38, which we can determine from the table 1. So, for tandem axial of 36 caves, we can calculate this. Standard axial caves is 36 caves, and this is the structural number, pavement structural number Sn. So, this table is the axial load equivalency factor for flexible pavement for tandem axial load, and the PT is 2.5 as per Ostrow 1993. So, for the axial load of 36 caves, this standard Sn value is equal to 6. So, here that is why Sn value 6 has been considered, and axial load equivalent factor is 1.38. So, for this axial load 36 and assumed value of 6, this axial load equivalent factor is 1.38. So, here axial load equivalent factor is equal to 1.38, which we have obtained from table 1. Hence, first year traffic estimate is equal to expected traffic into axial load equivalency factor. The expected traffic is 1 lakh into axial load equivalency factor is 1.38. So, 1 lakhs into 1.38 is equal to 138,000. So, this is the first year traffic estimate. Now, B, for analysis period of 25 years and no growth, traffic growth factor is equal to 25. This we have calculated from table 2. So, no growth factor for 25 years. This is from table 2. This is the traffic growth factor as per Ostrow 1993, and analysis for the period year is 25 and no growth, that is why this number will be traffic growth factor will be equal to 25. So, this is traffic growth factor is equal to 25. There is no growth, but for the analysis period of 25 years. Hence, W-18 will be equal to traffic growth factor into first year traffic estimate. So, growth factor is 25 into 138000, that means 34500000. So, this is W-18. Now, see, generally for most roadway DD is equal to 0.5, where DD is equal to a directional distribution factor. So, from the table 3, DL is equal to 0.90, the 2 lane in each direction. So, from this table 3, which gives lane distribution factor DL as per Oslo 1993. This number of lane in each direction, it may be 1, 2, 3, 4, and this is percentage of ESAL in design lane DL, that means 100, 80 to 100, 60 to 80, 50 to 75. Here we have considered a number of lane in each direction is 2, and percentage EL in the design lane DL 80 to 100, that we have considered here, that DL is approximately 0.90, that is 2 lane in each direction. Hence, W-18 will be equal to DD into DL into W-18, and DD we have calculated, that is 0.5 here, DL we have obtained from table, that is 0.90, and W-18 we have calculated earlier 345000. So, this will give this W-18 is equal to 1552500. Now, D table 4 helps to choose the reliability level, and from table 5 ZR is equal to minus 1.645 for R is equal to 0.95. So, we are choosing that this is the reliability, this table 4 suggested level of reliability as per Oslo 1993, and this is functional classification, interstate and other freeway, principal arterial, collector, local, and this recommended level of reliability capital R, whether it is urban or rural. So, depend upon this urban and rural. So, you can be able to obtain the reliability factor from this table. So, let us say this is interstate and other freeway, and this is the urban. So, we are considering some reliability factor which will lie between the 85 to 99.9. So, we are considering that reliability factor is equal to 0.95. So, for this 0.95 we have to calculate ZR value from table 5. So, ZR value you can calculate from table 5. This table shows the standard of normal deviation for different values of reliability. You can see reliability percentage starting from 50, 60, 70, 85, 90, 95, 99, 99.9, and correspondingly ZR value is given on the right hand side. Here, as we have considered the reliability is 95%, so ZR value is minus 1.645. So, for the 95% reliability, so ZR value we obtain from table 5 is equal to minus 1.645. Therefore, we can write FR is equal to 10 into minus ZR into S0, where S0 is the standard deviation, that means 10 into minus ZR value is minus 1645, and the S0 which we call the standard deviation, that is 0.35. So, if we calculate, we can have FR value will be equal to 3.764. Finally, W18 will be equal to W18 into FR, that means 155525000 into this FR, that means 3.764. So, this will give about 5.8 MSA, that is million standard axial. So, we obtain this finally W18 is 5.8 MSA, that you should remember. Now, step 2, determination of serviceability. Now, given PT, that means terminal serviceability is equal to 2.5 and P0 assume is 4.2 if not given. So, P0 is the initial design serviceability index. So, delta PSI will be equal to P0 minus PT, that means P0 is 4.2 minus PT is 2.5 is equal to 1.7. Now, step 3, determination of subgrade resilient modulus, that is MR. So, MR in PSI is 1500 into CBR, as CBR value is 2. So, 1500 into 2 is equal to 3000 PSI, or MR in terms of KPA it will be 6.89 into 1500 into CBR, that means 6.89 into 1500, CBR value is 2. So, it will give MR in kilopascal 20670 kilopascal. Step 4, determination of structural number, that is SN. The basic empirical equation for design of the flexible pavement by American Association for State Highway and Transportation, Oslo 1993 is as follow in FPS unit. This is W log 10 W18 is equal to ZR into S0 plus 9.36 into log 10 SN plus 1 minus 0.20 plus log 10 of delta PSI divided by 4.2 minus 1.5, this divided by 0.40 plus 1094 divided by Sn plus 1 whole to the power 5.19 plus 2.32 into log of 10 into MR minus 8.07. Now, we will use this equation. Here we know what is W18 is 5843610. ZR we have calculated, we have obtained ZR value is minus 1.645, and then we know that what is the value of S0, that is this S0, S0 is 0.35, that means standard deviation is 0.35 S0, and then delta PSI we calculated 1.7, and this MR value, this is MR value is equal to 3000 PSI. So, we can determine the structural number, that is S of n by trial and error method, or we can use the design chart which is also given. So, from the trial and error method you calculate that what will be the Sn value, and Sn value is here about 6.16, this is approximately 6.16. So, we assume 6 and we obtain about 6.16. So, this is the design chart for the CBR versus Sn for 1 to 10 MSA, and reliability factor R is equal to 95% and S0 is equal to 0.35. This is structural number versus CBR for different MSA. This may be 1 MSA, 2 MSA, 3 MSA, 5 MSA, 6 MSA, 8 MSA and 10 MSA. So, if we know that what will be the CBR value, and if you know that what will be the millions of standard axial, so you can determine what will be the structural number. In this problem, our CBR value is 2. So, you know in the x axis CBR 2, then we move up and we know that what will be this value. That means we know the MSA value, what will be the million standard axial, and here MSA value is about 5.8. This is W18, this is 5.8, that is million standard axial. So, this is 5.8. So, you can have the 5.8. This is the 5 in between 5 and 6. So, this is 5.8, and then you move horizontally, and then you can obtain what will be the standard structural number, that is Sn. So, this structural number Sn will be about 6.16. So, you can calculate that what will be the structural number which we obtained here 6.16. So, this is 6.16. Now, step 5, estimation of pavement thickness. For unreinforced case, Sn is equal to A1 D1 plus A2 D2 M2 plus A3 D3 M3, where D1, D2 and D3 are the thickness in inches of the surface, base and subbase respectively. A1, A2, A3 is structural layer coefficient for surface, base and subbase respectively. The layer coefficient depend upon the resilient modulus of the material. M2, M3 drainage coefficient for base course and subbase course respectively. As Sn value has already been determined in step 4, so D1, D2, D3 can be obtained by the trial and error method. Generally, the typical layer of coefficient used by the Oslo road test are as follow. A1 is equal to asphalt concrete surface course, that is equal to 0.40 to 0.44, A2 crushed stone base course, that is 0.10 to 0.14, and A3 sandy gravel subbase, that is 0.060 to 0.11. We obtain in our problem A1 is equal to 0.40, A2 is equal to 0.14, A3 is equal to 0.08, it is given. Now, drainage. Modified layer coefficient are used to account for the improved drainage condition, which is very important. Most of the time we do not consider the drainage condition, but we should consider the drainage condition. The quality of the drainage and the recommended drainage coefficient can be obtained from the table 6 and 7 respectively. As the drainage condition is good and pavement is exposed to saturation moisture more than 25% of the time, then we can obtain the M2 value is equal to 1.0 and M3 value is equal to 1.0. So, this is the drainage condition as per Oslo 1997. This is quality of drainage, whether excellent, good, fair, poor, very poor, and duration of the water removal 2 hours, 1 day, 1 week, 1 month, or water will not drain. We are considering that quality of the drainage may be the good and it is for the 1 day. And this is the table recommendation for M value as per Oslo 1993. This is quality of the drainage, say excellent, good, fair, poor or very poor. And this is the percentage of time pavement is exposed to moisture level approaching saturation. So, we have considered that moisture content it should be greater than equal to 25%. Therefore, recommended value for M is equal to 1 because quality of drainage is good. So, this is the 1. So, we are considering that subbase course and the base course is the same moisture content. So, this M2 and M3 value we are considering 1. Here you can see the moisture content in more than 25% of the time. So, M2 value is equal to 1.0, M3 value is equal to 1.0, because we have considered the subbase and base course is the same moisture content. So, we can obtain this moisture content. So, we have already calculated by trial and error that SN value is 6.16. So, we can write 6.16 is equal to A1 D1, that means 0.40 into D1 plus 0.14 into D2 into 1 is the moisture content M2, and plus 0.08 plus D3 into 1, this is M3 is equal to D3. So, if we calculate by the trial and error assuming the defined value and check up whether the left hand side will be on the right hand side. So, from this you can calculate what will be the thickness of the pavement. Assuming surface layer depth D1 is equal to 0.21 meter, assume the base course depth D2 is equal to 0.25 meter, hence you can determine the subbase depth D3 is equal to 0.47 meter. So, total thickness will be 0.21 meter plus 0.25 meter plus 0.47 meter is 0.93 meter. Now, step 6, design for reinforced case. For reinforced case, we know that Sn is equal to A1 D1 plus A2 D2 M2 plus LCR into A3 D3 M3, where LCR is equal to linear coefficient ratio. So, these are all are in inches. So, A1 we know, A2 know, A3 know is given, M2 know 1, M3 1. So, LCR value it depends on the California bearing ratio of subgrade and the type of the reinforcement used. So, we can obtain the linear coefficient value from this figure. This figure shows that we have used the geo composite, that is Geogrid and uneven geotextile, whose tensile strength is 40 kilonewton per meter. So, for the defined value of CBR, you can obtain the linear coefficient ratio LCR. Here CBR value is 2, so correspondingly that LCR value will be near about 1 to 1.5, it may be 1.4. So, LCR value we are considering that 1.4. So, if substitute this LCR value is equal to here 1.4. So, you know that LCR value. So, again you can calculate that assuming the surface layer depth D1 0.21 meter and base course depth D2 0.25 meter and subbase course depth D3 0.33. So, total thickness will be 0.21, 0.25, 0.33, that means 0.79 meter. You can see that thickness has reduced due to the deployment of the geosynthetic material. Step 7, saving of the subbase course material. The percentage of saving is unreinforced subbase depth minus reinforced subbase depth divided by unreinforced subbase depth into 100. That is percentage of saving is 0.47 minus 0.33 divided by 0.47 into 100. You can see saving about 28.57%. This is the pavement design without and with geosynthetic material for W8 is equal to 5.8 SMA. For in case of the conventional system where CBR is equal to 2%, so thickness of the pavement is 930 millimeter, and then you can divide it into subbase, base and the wearing course, that is subbase course is 470 millimeter, base course is 250 millimeter and the wearing course is 210 millimeter. And the right hand side we are showing that with the geosynthetic reinforcement system whose CBR value is 2%, and here is the geosynthetic material lies between the subbase and the subgrade material, and where the subbase is equal to 330 millimeter and the base course is about 250 millimeter and wearing course about 210 millimeter. So, you can see that how much we are saving of this good quality of aggregate with the deployment of the geosynthetics as a reinforcement material in unpaved road. With this I ended up this lecture today. Please let us hear from you. Any question? Thanks for listening.